My name is Neeraj Rajesh, and I'm here to talk about Apollo. Apollo is an ML-assisted real-time storage resource observer. It has a high-performance data store custom-made for telemetry data that supports fast querying and low-latency access on telemetry data. It maintains a low cost of resource monitoring by supporting adaptive and dynamic monitoring intervals, and still maintains high accuracy using ML assistance. It supports in-situ high-level knowledge extraction, where we create high-level composite I/O metrics using low-level hardware counters, and we also simplify the usage of telemetry data by the disengagement of the composite metric computation to the monitoring service. On designing Apollo, we meet some key observations. Applications and I/O libraries often depend on the current view of the computing environment to make optimal decisions. Data placement engines, replication engines, prefetching engines all need to know the remaining capacity of a storage tier as well as the performance of each tier. Telemetry data collection must balance accuracy and timeliness while still being fast and lightweight. Existing monitoring tools focus on monitoring from an administrative perspective. Telemetry data is stored in an SQL or a NoSQL database, and they have an ability to visualize the status of the system. And the data collected is usually used for offline data analysis to find application bottlenecks post-runtime. And so we see the existing monitoring tools have certain limitations. From an application perspective, there is a lack of access to this recent telemetry data that has been collected with low latency. Also, there is a lack of a way to monitor these resources exclusively managed by an application. From the serving perspective, the serving layer cannot service these highly concurrent requests for the system status. Data collection, data curation, and data serving act independently, and this introduces certain latency. From the monitoring perspective, there is an inability to adapt to dramatic fluctuations in this telemetry data being collected. Also, low-level resource metrics alone cannot explain the status of the resource. And so this leads to a multitude of different metrics needing to be collected by the application. From these observations, we can summarize that stale telemetry data is useless data. Applications need this data on time. We also see that raw telemetry data is useless data. These low-level hardware counters provide very limited value and require specialized knowledge in order for you to extract meaningful information about this monitored resource. And then costly telemetry data is useless. High resolution monitoring leads to increased accuracy for telemetry data, but this also demonstrates high overheads. So with this, we designed Apollo. Apollo was designed to achieve two main objectives. First, it was designed to aid applications in making optimal decisions by maintaining a current view of the system. So it does this with a decoupled and parallel computation paradigm, and by the disengagement of the composite metric computation to the monitoring service. Then it aims to reduce the overall cost of resource monitoring while still increasing accuracy. It does this by using adaptive and dynamic monitoring intervals and using machine learning to increase data resolution. Here is how Apollo is deployed. The yellow circles are the inside vertices and the blue circles are the fact vertices. The application interacts with the Apollo API and sends in queries. And then the fact vertices collect metrics from these different resources in the cluster. At a high level, Apollo uses SCORE. Applications submits query to the Apollo query engine using the Apollo API, and the Apollo query engine distributes these queries to these different vertices to get the different information that's been asked for, and then aggregates them. The Apollo core is a DAG of these fact vertices and insight vertices here. Now we get into the node level details. We need to establish certain primitives. We have a fact, which is the low-level metric. It's a simple metric. The insight, the composite metrics, which are made up using facts or other insights. Then we have certain abstractions. We have fact vertices, which deal with the collection of facts. We have insight vertices, which deal with the aggregation of facts and our insights. And then we have Delphi here. Delphi is the ML model that aids to increase the resolution of the monitoring data. To demonstrate the flow of events, metrics are collected by the monitoring hooks, which pass them on to the fact builder, which adds a timestamp and then adds it to the back of the fact queue. The insight vertex pulls in facts from the fact vertex and from other insight vertices, builds the insight where it applies a function on top of this data collected, and then stores it in the insight queue. Now, when applications query Apollo, the fact query executor and the insight query executor are responsible for dealing with the query and providing the necessary data. Now we get into the design of our improved storage layer, SCORE, and also how we create these I/O insight curators. Abbreviated for Storage Condition Report, SCORE is the core data structure of Apollo. It has a decoupled design, and its implementation is based on using distributed lock-free queues. SCORE has two key components, the fact vertices, which collect raw data, and the insight vertices, which make information from collected data or other information. With SCORE, we achieve low latency data access and distributed and parallel data querying. The I/O curated insight is a composite metric made of other metrics. This is because low-level metrics individually do not reveal the full picture about the system. Applications can use I/O-specific insights to offload computation and in-depth understanding of low-level metrics to create composite metrics. These I/O insights can also be used to make data placement decisions, decisions on resource allocation, and even general decisions for coordination. In order to achieve high accuracy with low monitoring costs, we came up with adaptive and dynamic monitoring intervals. While polling each metric, there needs to be a balance between the polling frequency and the overhead it creates. Polling more obviously creates a significant bottleneck. Polling less, however, presents a risk that could miss vital information. It would be more effective to adapt the polling interval based on how the metric is changing. This provides a reasonably up-to-date information of the resource while still minimizing the monitoring cost. To do this, we use the simple additive increase, multiplicative decrease method, where the interval changes based on a constant additive increase or a multiplicative decrease. And this is based on a threshold. If it is below the threshold, the interval is increased by an additive constant, and if it is above the threshold, it is decreased by a multiplicative constant. And then to build up on top of this, we came up with the complex additive increase multiplicative decrease method, which uses a rolling average of changes instead of using a single change. And this accounts for metrics that just randomly spike and come back to a general baseline. Our intuition with Delphi was that a lot of these metrics follow a time series. And so we created a time series model that have 5 key patterns, which ultimately fall into 8 features. And we made a model for each of these patterns using synthetic data. With the synthetic data of each of those 8 features, we trained 8 independent time series models. And then we stacked those 8 models as shown in this architecture diagram here. We then froze the pre-trained layers, and we added a miscellaneous layer which picks up on subtle feature changes that were missing in this dataset. And then this model was once again trained on a complex synthetic dataset. Here and in this figure, we see the inference time and the different dataset metrics. On top of that, we noticed that we didn't need all 8 models, and we could shrink that down to 5 models that were still effective in predicting the different features. And now we came to the evaluation of our design. Our testbed consisted of 32 compute nodes and 32 storage nodes, with a network of 40 gigabits per second, and with the following software stack. Our evaluation plan focused on the overall resource consumption overhead of Apollo, to quantify how we balance the access latency and the I/O throughput, to see how effectively we are balancing the cost of monitoring and accuracy of the data, and also some real evaluations. Here we quantify the resource consumption and overhead of Apollo. We can see that the CPU overhead compared against tools like PAT, SAR, and IOR, and they're pretty comparable. And then we also compare the overhead that Apollo poses on the memory, and we see it's not that much. Next, we need to evaluate our design for SCORE. We first need to test the internal components of SCORE. This is done to establish a lower bound of our expectations for how fast SCORE can go. For the fact vertex, we see that the monitoring hook takes 97% of the time, and in total it takes close to 16 milliseconds to publish a fact. For the inside vertex, we see that we see a lot more things happening clearly because it doesn't have the main bottleneck, which is the monitoring hook. This whole operation takes place in close to half a millisecond. Next, we need to evaluate the throughput of the consumption and production of data to and from SCORE. So for this first test, we measured the throughput while scaling the number of clients connected to SCORE that consume telemetry data from Apollo. On the y-axis, we have the throughput in messages per second, and in the x-axis, we have the number of clients connected. Similarly, in this test, we scale the production of telemetry data by the number of monitoring hooks, and we see that the throughput increases as we increase the number of hooks to a point, and then it kind of flatlines towards 40 monitoring hooks. Next, we evaluate the scaling of the Hamming distance and the node degree. The Hamming distance is the maximum number of hops possible in a network. The node degree is the number of connections to other nodes incident on a particular node. On the x-axis here, we scale the number of nodes for the Hamming distance, and similarly here for the node degree. And on the y-axis, we show the latency per event in milliseconds for both of them. In this test where we scale the Hamming distance, we see that up to a Hamming distance of 8, it has a latency of sub 1 millisecond. And as the Hamming distance approaches 16, it reaches a little above 1, and once it hits 32, it's beyond 6 milliseconds per event. And this is expected as the message needs to hop over multiple nodes to reach its final destination, and each node adds a little bit of latency to the next hop. Similarly, on scaling the degree of the node, we see that the latency per event is still less than 0.15 milliseconds for even 640, even for a node with a degree of 640 nodes. This shows us that even while scaling the Hamming distance and node degree, SCORE is capable of providing low latency data access to telemetry data. Next, we evaluate how we balance the cost of monitoring and the accuracy of data in Apollo. We need to test the effectiveness of the adaptive and dynamic monitoring module. In the y-axis, we have two sets of applications: a regular hack run and an irregular hack run. And then we also have the different intervals the monitoring was done at. We have a fixed 5-second monitoring. We have the simple AIMD and the complex AIMD for both sets of applications, and then we have the accuracy, which is basically defined as the ratio of changes that we saw versus the changes that happened. The cost metric is dependent on the overhead it posed on the system to determine the next interval, and also the number of measurements it took. So one observation we made was if you pick a good fixed interval for a regular workload, you are fine. You will have good accuracy without any other additional overhead. The simple and the complex AIMD did not do as well compared to the fixed interval because the 5-second mark was the ideal point, while the simple and the complex AIMD did not perform as well, and the complex AIMD with a significantly higher cost. Compared to the irregular workload, we see the fixed 5-second interval have the lowest accuracy compared to the simple and the complex AIMD, with the simple AIMD having the least cost of the two, and the complex having the most, while the complex still having the most accuracy. And so we see that there are several factors that can affect the adaptive and dynamic monitoring intervals, and we notice that its main effectiveness is in irregular workloads. Next, we see how Apollo can aid in reducing the overall cost of resource monitoring while increasing the accuracy. We again have we here have an irregular workload that was run for a certain amount of time. There is a green line here behind that, which is Apollo without Delphi, and since that follows the baseline very closely, it is right behind there. And then we see Delphi having certain spikes and errors in its prediction, but ultimately rectifies itself as time goes on. The cost of monitoring, we see that the baseline model is very expensive, whereas Apollo, without Delphi, can still provide us with the same level of accuracy at a fraction of the cost. And then we can use Delphi on top of that to further reduce the... here we also do a similar comparison with a regular workload, and we see that Apollo is once again able to reduce the overall cost of monitoring while still maintaining the accuracy. Next, we have some real evaluations. Here we compare Apollo with the Lightweight Distributed Metric Service, or LDMS. We also have some real-world applications. In comparison with LDMS, we scaled the number of client nodes, and we measure the average latency as in the x and y axes respectively. And we see that Apollo scales much better than LDMS as the number of clients increase. In terms of the average CPU overhead, we see that Apollo has a slightly higher overhead in terms of CPU cycles, but we also have seen that we scale better, and we also are pretty comparable in other aspects of the client storage overhead. Then additionally, we also compared the scaling of the query complexity against LDMS. The complexity of the query increases with the number of joins. And so we have the number of joins in the query being scaled on the x-axis and the execution time on the y-axis. And so we see that Apollo still performs reasonably well against LDMS. Next, we need to quantify how the awareness of the status of the storage resources is vital to the performance of middleware libraries. In this, we run different applications. The vpik.io kernel, which writes 32 megabytes per process, the BDCats, which reads the data generated by vpik.io, and then lastly, Montage, which is a collection of MPI programs that read 10 megabytes of data per process. We run these applications on a scale of 2,560 processes, with and without different middleware libraries. We first ran them on bare on the PFS to establish a baseline, and then we run them with the middleware library without Apollo. We use Apollo to aid the middleware libraries in making resource-aware decisions. Here, we use Apollo to maintain a metric that keeps track of the performance of different storage tiers, as well as the capacity of different storage tiers, that aids these middleware libraries in making effective decisions. And we can clearly see a performance improvement between these three middleware libraries. In conclusion, we have created Apollo, an ML-assisted real-time storage resource observer, and we show that Apollo has a serving and querying layer that is capable of serving telemetry data with low latency and high throughput. Apollo has 3 times lower latency compared to LDMS, while only having a 7% increase in overhead with a higher monitoring data resolution. We also show a reduction in the overall cost of monitoring by roughly 10 times by using an adaptive and dynamic monitoring interval, along with the machine learning model Delphi, while still providing high-resolution telemetry data. We also show that applications can use Apollo to offset some overheads in decision-making, while still being resource-aware with the help of I/O curators by approximately 10 to 15%. For the future work, we see that adaptive and dynamic monitoring still has certain limitations. It only works when the change in metric is observed, and the heuristic used could be a little more intricate. We could also improve the way monitoring is done using K-probes, and this reduces the minimum monitoring bound and also lowers the overhead. Thank you. I hope you enjoyed my talk. You can find Apollo on the following Git link. My name is Neeraj Rajesh, and feel free to reach out to me if you have any questions. Thank you.